The electromechanical relay, or EMR, is an electrically powered switch that uses an electromagnet to provide the force to close or open switch contacts. A diagram of a simple relay is shown in Figure A. When the electromagnet, called the coil, is energized, it pulls down on the spring-loaded armature. Relay contacts are described as being one of two kinds: normally open contacts, NO, which are open in the unenergized state, and normally closed contacts, NC, which are closed in the unenergized state. Figure B shows one common schematic symbol for the relay. By convention, the symbol always depicts the relay in the unenergized state, so you can easily determine which are the normally closed and normally open contacts from the schematic. Another schematic representation for the relay is shown in Figure C. This symbol is used in a type of drawing called a ladder diagram. In a ladder diagram, the relay coil and its contacts are separated on the drawing. We will see more about ladder diagrams in chapters 9 and 12. The electrical specifications for the contacts are different than for the coil. For the contacts, the maximum current and voltage for DC and AC operation is specified. For the coil, the intended voltage and coil resistance are usually specified, and you can see these numbers on the specification of the spec sheet shown in the table. The coil voltage and resistance can be used to calculate the steady-state coil current. Actually, it takes more voltage and current to pull in the relay contacts than it does to hold them there, because the armature must be pulled across the air gap. Hence, these quantities are called respectively the pull-in voltage and the pull-in current. For example, the contacts of a particular 6-volt relay actually close at 2.1 volts and stay closed until the voltage is decreased to 1 volt. Notice that the actual pull-in voltage is much less than the rated coil voltage. This is to guarantee that the relay will pull in quickly and reliably when operated at the rated voltage. The values of voltage and current needed to keep the relay energized are called the minimum holding voltage and the sealed current. Coil voltages are specified to be either AC or DC. The difference is that the AC coils are constructed with shaded poles to prevent buzzing with 60 Hz power. The shaded pole relay has a metal ring around the pole face of the electromagnet. Magnetic flux induced in this ring keeps the relay closed when the AC cycle goes through 0 volts. Relays are available in a variety of sizes, contact configurations, and power handling capabilities. Some miniature relays can plug into an IC socket and be powered directly from a digital logic gate. On the other end of the spectrum, a power relay, often called a contactor, is used to switch the current directly to large machines and may handle many hundreds of amps. It is well to remember that for two reasons relays have a finite life. First, because the relay is a mechanical device, the moving parts eventually wear out. And second, the electrical contacts can become pitted because of arcing. The contact wear is very dependent on the electric current that is being switched. For example, a certain relay is rated for 9 million operations at 1.5 amps, but only 2 million operations at 3 amps. 2 million operations sounds like a lot, but if this relay were in a 24-hour factory being used in a repetitive operation every 10 seconds, it would have to be replaced every 8 months. Contact life is also dependent on the type of load being controlled. For example, inductive loads such as motors cause much more arcing and pitting than resistive loads such as lights and heating elements. The reed relay is unique because the small reed-like contacts are encapsulated in a small sealed glass tube that is either evacuated or filled with an inert gas like dry nitrogen. The contacts are activated by an external magnetic field as shown. Contacts are either dry or mercury wetted. Mercury wetted contacts have a thin coating of mercury that fills in surface irregularities, making a larger conduction area and reduces pitting. Generally, reed relays have a long life and low coil voltage, frequently TTL compatible, and are immune to dirty environments. However, they are generally low power for contacts rated at 2 amps or less and are vibration sensitive. We move on now to solid-state relays. A solid-state relay, SSR, is a purely solid-state device that has replaced the electromechanical relay in many applications, particularly for turning on and off AC loads such as motors. Physically, the SSR is packaged in a box about the same size as an EMR, with 4 electrical terminals as shown in Figure A. The 2 input terminals are analogous to the coil of an EMR, and the 2 output terminals are analogous to the contacts of the EMR, usually single pole, single throw, normally open. The input or control voltage to the SSR is typically 5 volts DC, 24 volts DC, or 120 volts AC. The 5 volt DC models are designed to be driven directly from TTL digital logic circuits. Turning our attention to the output side of the SSR, we see that the load is placed in series with the 120 volt AC or 240 volt AC power. The output current can be as high as 50 amps in some models. Many SSRs incorporate a feature called zero voltage switching. The line current is switched on at the precise time that the AC voltage is crossing 0 volts. This eliminates sharp output voltage rises times and so minimizes electromagnetic interference noise, or EMI. Figure B shows a block diagram of the interior of an SSR. The input voltage drives an LED, a light-emitting diode, and the light from the LED turns on a phototransistor, which in turn turns on the TRIAC, a solid-state switching device discussed later in this chapter. The LED electrically isolates the input and output sections of the SSR. This is important for 2 reasons. First, it allows the control electronics to have a separate ground from the power lines. And second, it prevents high voltage spikes in the power circuit from working their way back upstream to the more delicate control electronics. Many SSRs incorporate a feature called zero voltage switching. The line current is switched on at the precise time that the AC voltage is crossing 0 volts. This eliminates sharp output voltage rise times and so minimizes electromagnetic interference noise, or EMI. I've just said that actually. Solid-state relays have a number of important advantages over electromechanical relays. Having no moving parts means that, theoretically, they will never wear out and makes them practically immune to shock and vibration. Also, because of the built-in electronics, they can be driven with a low voltage source, such as a TTL, regardless of the output current capability. The main disadvantages of the SSR are the following. They can be false triggered by electrical noise. Even when on, the output resistance is not exactly 0 ohms, so there's some small voltage drop and consequent power loss within the relay. And when off, they may have lethal levels of leakage current. Although they are long-lasting, unlike an EMR, they do not fail predictably. Contact arrangements are limited, so they may not work for all relay applications. Some circuits call for normally closed and/or auxiliary switches on the same switch. The hybrid solid-state relay is similar to the SSR, but uses a low-voltage, fast-acting reed relay instead of an LED to turn on the output TRIAC. Using the reed relay provides good electrical isolation and may work better than the SSR in some situations.